Hi, how are you doing? I'm Monica Gracida, and I'm going to stream for Fiveable Properties of Solids. Could you, how are you doing today? Could you give me an emoji or a thumbs up to show me how are you doing today? Good, Serene. Okay, let's get this stream started. Thank you. I would like to start this stream by, hi Beverly. Okay, we are going to, don't forget to follow us in social media. Today we're going to learn a little bit more about crystalline and amorphous solids and the different kinds of crystalline solids. To start the stream, could you please answer the 3 polls that appear at the bottom of your screen? If you go to the bottom of the screen in polls, you can click on it and 3 questions will appear. Could you please answer them for me? Hi, Sergio. So the first task is to answer the 3 polls that are on the bottom section of the screen. Okay, so 3 of you already answer if the one of ionic solids are brittle or malleable. 2 of you answer, do molecular solids conduct electricity? But only 1 of you answered the one of classification of plastics. So we're going to leave those answers pending, and then we're going to answer them throughout the stream. Okay, so the first distinction that we're going to do is crystalline versus amorphous solids. Crystalline solids are arranged in an orderly fashion. They form a crystal lattice. They have a specific geometric shape with defined edges. They have a specific temperature for its melting points and for its boiling points, for that matter. They will have a long order arrangement of particles. What does that mean? That their structure will go on and on and on with the same particularity. And they break or cleavage along particular points. And when we think of solids, we're actually thinking of the characteristics of crystalline solids. Okay, examples of crystalline solids, crystals like the ones that you can see on like mineral crystals, copper wire, for example, a diamond, ice or snowflakes are all examples of crystalline solids. Amorphous solids, on the other hand, their particles are randomly organized. They don't have any particular geometry in their shape. They don't have a specific melting point. They have a range of temperatures in which they will boil or melt. Their order of arrangement is short, and it can change. It can change the arrangement. They cleavage or break into uneven parts, and they're also known as super cool liquids. Could you think of a solid that has these characteristics? Could you think of an example? Okay, yes, a water bottle would be an amorphous solid, correct? Excellent, Matthew, thank you. Yes, examples of amorphous solids would be like wax, like plastics. Why? Okay, Serene, why are they called supercooled liquids if it's a solid? If you think, for example, of glass, It's actually, how do you make glass? You first melt the substances that you're placing together, and then you cool them. That's why they're called super cool liquids, because they have more characteristics of a liquid than as a solid. Their arrangement is not so organized, just as liquids are. Like they are not so. Remember that solids are very close together, their particles, and liquids, they're not so close together in their particles. That's why. So maybe the examples can help you. Like wax, it's very easy to melt it, and then you solidify it and you will get this candle shape. Or glass, or plastics. Exactly, they do not have a crystal lattice because they're not arranged in an orderly pattern. Yes, exactly, well done. Thank you, Siri. Okay, so any other question about amorphous solids? Okay, we're going to move on. Now we're going to see characteristics of crystalline solids. We're going to focus now on crystalline solids. And crystalline solids are classified according to what do you have on the lattice point. So if you have ions on the lattice points, it will be an ionic solid. We're going to talk about the lattice point in a moment. If you have molecules, they will be called molecular solids. If you have atoms, they will be called atomic solids. So it's really straightforward, the category. So for example, an ionic solid, we will have ions on the lattice points. And the lattice points, you can think of them of the corners of the cell, of the unit cell. So for example, this one, for example, for sodium chloride, we already know that sodium chloride bonds with a ratio of 1 and 1. So if we think of this structure of 1 to 1, you will have a crystal lattice where each sodium ion will be arranged or surrounded by 6 chlorine ions in 3D. And the chlorine ions will be surrounded by 6 sodium ions. Why 6? Because we have to think of 3D. With one on front, one on the back, one on the top, one below, and one on each side. So that's why we will have 6 per unit, but in reality, we'll have an overall ratio of 1 to 1. Structures that have a 1 to 1 strict arrangement, they will have a cubic arrangement. Like salt, if you really observe your salt tomorrow or today at dinner, please observe the crystals of salt when you eat your dinner. If you observe them closely, what do they look like? What shape do they have? Have you noticed that? Have you noticed your salt when you eat it? Exactly, Beverly. They will look like cubes, like tiny cubes, if you look closely. If you have rock salt, you will see that their cubes like overlap to each other or clustered with each other. And that type of structure is because the ratio is a 1-to-1 structure ratio. All binary ionic compounds that are formed from an alkali metal and a halogen will have this structure because all of them will have a ratio of 1-to-1. Except for cesium, because cesium is a very large metal. So this arrangement, this cubic arrangement, is also called a sodium chloride structure. Okay. If we don't have a ratio of 1-to-1, like in this model show us, then we won't have a cubic arrangement. We will have all sorts of different and beautiful arrangements that we have with mineral crystals that we found on Earth. Okay, so as we mentioned already, you have ions on the lattice points, and something to notice, something interesting to notice is, do you notice the smaller size, slightly smaller size of the sodium ions? Here on this diagram, we're missing the plus sign on the sodium. This is a sodium ion, so it must have a sodium +1. Do you notice the difference in size? Do you remember what causes this difference? Do you know what causes this difference in size? If you remember the periodic table, both sodium and chloride are located in the same period. So what causes this difference in size of the radius? What happens to sodium, to the sodium atom, to be able to convert to a sodium ion? What happens to the electrons? Excellent. Yes, Matthew. The sodium atom has to lose electrons to be able to transform into a sodium ion. And not only electrons, but its valence electrons. It loses its outer shell. If it loses its outer shell of electrons, but doesn't lose the protons inside the nucleus will have more attraction towards the valence electrons. So the sodium ion gets a little bit smaller, well, much, much smaller, almost half of its size than the sodium atom. With this reasoning, what do you think will happen, or why, what happens to the chloride ion compared to the chloride atom? Chlorine atom, what does it has to do? Yes, Matthew. It has to gain an electron. So now the valence electrons are increasing and the protons are not changing. So now the protons are not able to hold those electrons closer and the radius of the ion grows. So we will have a smaller sodium ion and a larger chlorine ion. How does this help on the crystal lattice? It helps because now the sodium ions could accommodate or make their way into these spaces of the chlorine. So they're going to be closer together to each other, creating a greater attraction or a stronger structure. So this takes us with the concept of lattice energy. Okay, Matthew, here we are not talking about intermolecular forces, it's intramolecular, because the ionic bond forms electrostatic attraction between the sodium and the chloride ion. So that's an ionic bond. It's actually an intramolecular, between atoms. The force is between the atoms. Intermolecular forces, we see them with covalent bonds. When molecule A, it's attracted to molecule B. But here we don't have a molecule, we have an ionic bond. So in here, we're not dealing with intermolecular attractions. Okay. So the lattice energy, which you could think of the force that keeps these ions together. Correct, Serene. Within molecules, or in this case, ions, would be the intramolecular force, right? Because molecules are synonyms for covalent bonds. And right now, in ionic solids, we're dealing with ionic bonds, not covalent. But yes, it would be within the ions. Correct. Excellent. Okay, so the lattice energy would be a calculation of how strong is this force that keeps them together. And the lattice energy could be calculated using the following equation, that it's a modification of Coulomb's law. The lattice energy would be a proportionality constant that it depends on the structure of the solid and the configuration of the ions, and the charges of the ions that are making this lattice divided by the radius. So the smaller the radius, the greater the lattice energy, and the greater the charges, the greater the lattice energy. So if we go to the same reasoning, sodium and chloride are on the third period of the periodic table. Do you remember in which period are the elements lithium and fluorine located? You could go or open a tab with ptable.com if you want to see the periodic table, if you don't have one at hand. Sorry, I moved there. Okay. ptable.com. I want to write it down here. ptable.com. You can go to it and it will show the periodic table if you don't have one at hand. So lithium and fluoride ions, in which period of the periodic table are they located? Well, another way of seeing it, in period 2, Matthew, correct. Will these ions be smaller or greater in size than the ones of sodium and chloride? Lithium, would it be smaller than sodium or greater than sodium? Chlorine is greater, correct? Versus fluorine. Fluorine is smaller than chloride. And sodium is bigger. Lithium is a smaller, much smaller than sodium. So what effect will this have on the crystal lattice would be that, what do you think, which one of these two, will sodium chloride or lithium chloride, which one will have a greater crystal lattice? A crystal energy, I'm sorry, a lattice energy. Which one of these two salts will have a greater lattice energy? Sodium chloride or lithium fluoride? Okay, remember, the smaller the radius, if we look here at the equation, the smaller the radius will give us a greater lattice energy. So in this case, lithium fluoride will have a greater lattice energy because both of the ions are smaller. Why does that matter? Because then they're going to be closer to each other and the attraction will be greater just because they're closer to each other. Does this make sense? Okay, excellent. Let's move on. Okay, another quality or characteristics of ionic solids is most of them dissolve in water. For example, sodium chloride, all of you have tasted, for example, soup where it's salty. So salt dissolves in water very, very easily. Why? Because water is a polar molecule. That means, if you remember, that hydrogen has a partial positive sign and oxygen a partial negative. So this one organizes or ionizes the salt in the way of all the sodium ions will like break apart from the solid and will be surrounded by water molecules. And the water molecules will align themselves so that the negative part is facing the sodium ion. And then the opposite will happen with chlorine. The chlorine ions will break free of this solid and they will be surrounded by the hydrogen ions that are positive. So this is how water ionizes or breaks apart the ions of the solid sodium chloride. Does this make sense? Okay, excellent. Let's move on. But we know of some ionic solids that do not dissolve in water. Why do you think this is? For example, most of the carbonates do not dissolve in water. When you place them in water, they go to the bottom and you are not able to make them soluble. Why do you think that is? Think in the terms of the lattice energy. We mentioned that the lattice energy depends on what? On the radius and on what other thing? Let's go back to that slide of the lattice energy. The lattice energy depends on the radius and the Qs. The Qs are the charges of the ions. So if you have large charges, then they will have a greater lattice energy. And what happens is that they are more attracted to each other, to the ions, that this effect of water doesn't have any effect on these really, really strong crystal lattices or with this great lattice energy. They prefer to be with each other, stuck with each other, than to dissipate with the water. So it has to do with the strength of the lattice energy. Does this make sense? Excellent. So usually ions with a ratio, with a charge of +1 or -1, they will dissolve, but ionic solids with charges greater, +2, +3, some of them won't be able to be soluble on water. Okay, excellent. Let's move on. Okay, so do you think ionic solids can conduct electricity? Imagine I draw here a beaker or just a plate with sodium chloride crystals. I draw here some electrodes and some wire, and of course you need a battery. If not, you won't be able to make the electrons move, and a flashlight or a light bulb, sorry. Do you think the light bulb will turn on if it's connected in this way? Okay, Matthew, no. Why? Why do you think it won't be able to light up, the light bulb? Well, first of all, what is the definition of electricity? How do you get light from a light bulb? What has to happen? Okay, electricity, yes, it's kind of a charge. Electricity, the definition, it's a flow of electrons. So the electrons need to flow. In here, the sodium chloride crystals in a solid form, they won't be able to flow. They're stuck together with themselves. They're bonded with themselves with a strong crystal lattice. So they won't move towards the electrodes to make this flow of electricity needed for electricity to flow. So correct. Ionic solids in crystals won't be able to conduct electricity. But what will happen if I melt the salt crystals and try again? Do you think now the light bulb will light up? Yes, yes, Matthew, you're right. The light bulb will now be lit and will lit up. Why? Because now the ions are able to move. Since it is melted, the ions are able to move towards the electrodes, creating this flow of electrons or closing the circuit, and the light bulb will be able to light. Very good. Okay, what do you think will happen if we dissolve sodium chloride in water and place again the same system? Do you think the light bulb will light up now with sodium chloride dissolved in water? Okay, why? Matthew says yes, it will light up, but why? Think of the ions. Are the ions in sodium chloride easy to flow? Yes, yes, Matthew, you're correct. Now the ions are easy, are free to flow. They're free to flow. They jump into the electrodes, and that causes a flow of the electrons in the wire. And yes, the light bulb will light up. Excellent. Okay. So yes, ionic compounds will conduct electricity when they're melted or dissolved in water, but they won't if they are in the solid form, because in here the ions are trapped and they cannot move around to make this flow of charge. Okay, now what would happen to ionic solids when a force is exerted on them? Suppose that these are the crystals and I take a hammer and I hammer the sodium chloride. I apply a force to it. What do you think will happen? Would the crystal break or it will stay the same? Okay, Matthew, you're saying it will stay the same. Why? Okay, so because of the crystal lattice, okay, let's see what happens. If I heat the crystal lattice of sodium chloride from here, what will happen? The force could be enough to slide or move a little bit the ions. And now, instead of having a sodium and a chloride, I will have two chlorides together with a negative charge. What happens to the to things that have the same charge? Will they repel or attract? Exactly, same charge will repel. So then they will have a repulsion for a repulsion in that point, and it will break apart. So it will break apart. What is this property called? This property where the solids break apart when a force is exerted on them. I mentioned it in the polls. If you haven't answered the polls, you can go ahead and answer the polls that are on the bottom of your screen, where I asked about, I made some questions about these concepts. Exactly. Yes, Matthew. This property of ionic solids is called brittle. So ionic solids are brittle, which means that they break apart when a force is applied on them. And they will break apart because of these repulsion forces that we are causing by aligning the same charges. Excellent. Okay, so now that we reviewed ionic solids, can you give me some of the properties? So in general, ionic solids will have high or low melting points. Think of the lattice energy. Will you need high temperatures to melt them or not really? Correct. We will have high melting points because they are, remember that they want to be together. Their lattice energy is usually very, very high. So the the melting point will be regularly high. What about the boiling points? High or low? Exactly, the same. They will have high melting and high boiling points. What about electricity? We already talked a little bit about electricity. Will ionic solids conduct electricity? Remember, it was yes, if. What are the if points here? Correct. They will conduct electricity if electrons are able to flow freely. How do we know if they will flow freely? You will know if they will flow freely if they are melted or if they are dissolved in water. Excellent. Let's move on. Okay, we're going to switch to molecular solids. Molecular solids, as the name is saying, they will have molecules at the lattice points. Remember, ionic solids have ions on the lattice points. Now we have molecules, so covalent compounds will be on the lattice points. For example, ice. In ice, we have molecules of water in the lattice point. So remember, this is an oxygen molecule attached to two hydrogen ions. And now we do have intermolecular forces acting on them because this is a covalent compound. So now molecule A, which we'll have here with one oxygen and two hydrogens, will be attracted to molecule B by intermolecular forces. This intermolecular force is called a hydrogen bond because a hydrogen it's involved with oxygen in this case. And now the ice forms a lattice where it's arranged in this way. When you place ice in water, if you're drinking a glass of water and you place ice, what happens to the ice? Does it float or does it sink? Correct. Ice floats in water because it forms this open structure this open structure, that it will be less dense than liquid water, and that's why ice floats in water. Excellent. Okay, another example of a molecular solid will be sucrose, like table sugar, regular sugar. Sugar also has in its molecules some oxygens with hydrogens. It has carbon atoms, the black spheres. It has hydrogen, the white spheres. It has oxygen, the red ones. So oxygen and hydrogen again. So we have some parts that are able to create hydrogen bonds. So when sugar forms sugar crystals, what happens is that the ionic bonds get organized so that you can have an oxygen on one side attracted to a hydrogen on the other molecule. So when you have sugar, it will be arranged in a certain way where they have these intermolecular attractions between them. Does this make sense? Okay, so how does sugar dissolve in water? When sugar dissolves in water, it also interacts, the intermolecular forces also interact with water, and water molecule surrounds the sugar. But the difference here is that the molecule is not broken apart into ions because there's no ions here. It just gets organized or aligned with the partial positive of the sucrose would be surrounded by partial negative of the water and vice versa. So the whole chunk of sucrose will be broken apart from the crystals, but it will maintain its structure or its identity. So can molecular solids conduct electricity? If you have sugar crystals and with this same system of the electrodes and the wire and the light bulb and the battery, do you think it would be able to conduct electricity? That's right. That's right, Matthew. It won't be able to conduct electricity. Why? Because we don't have ions or no charges to flow, right? The molecule stays as a whole. So, and what about molten sugar? Do you think molten sugar would be able to conduct electricity? Exactly, no. What about dissolving water? Okay, so dissolving water, no, dissolving water, I'm sorry. Canela. Okay, dissolving water, it won't be able to conduct electricity because the molecule will stay together. It won't dissociate. There's no ions to dissociate in the first place. The molecule is bonded with covalent bonds and it will stay as a whole. Okay, so molecular solids will not conduct electricity in any form. Okay, now, what happens to molecular solids when a force is exerted on them? Would it break apart or would it stay together? Okay, I showed here, my drawings are not so good, but I'm trying to show here a structure of sucrose and the intermolecular attractions, the hydrogen bonds between one molecule and the other. Do you think this force will be able to break these bonds, these intermolecular forces? Okay, the answer is yes, it would be able to break them apart, and then we will have two pieces of crystals. So molecular solids are also considered brittle. You can break them apart when a force is exerted on them. Okay, let's do a review. So compared to ionic solids, will molecular solids have high or low melting points? Think of the force that keeps them together. The force is an intermolecular force, and the ionic is the ionic bond. Which one is stronger? Will molecular solids have high or low melting points? Exactly. Molecular solids will have low melting and boiling points because the intermolecular attraction that keeps the crystals together is weaker than a force created by an ionic bond. Will molecular solids conduct electricity? No. Even if we melt them? Even if we melt them, it won't conduct electricity in any form, correct? And are molecular solids malleable or brittle? Exactly. Excellent. Excellent review for molecular solids. Let's move on. Okay, we are now to the third type of crystalline solids, which are atomic solids. These one have a subcategory that are metallic solids or network solids. We're going to start with metallic solids. In metallic solids, as you can infer, it will have metals in their lattice points. In this case, the metal atoms get organized in this way. The core or the nuclei and the core electrons stay in the same place, stay put. But the valence electron of each metal atom is able to be loose around, to flow easily into, it's like distributed, it's like shared between all the cations. So it forms, this model right here is called the model of the sea of electrons. And what it's explaining here, what it wants to explain here is that the valence electrons of the metal atoms are not bound to the nucleus. They can be, they are loose, they are shared or loose into all the cations. So, for example, imagine this is a zoom in of the atoms in a spoon, of a metal spoon. And you are holding the spoon from one end and you're heating directly on the stove the other end of the spoon. What do you think will happen? Will you get burned with the spoon or nothing will happen? Will the heat of the fire be conducted through the metal? Exactly. Yes, you would even have to let go of the spoon because since electrons flow, if the electrons that are here directed to the heat of the flame, they can move around and pass this movement around to where your hand is. So yes, because of this explanation of the sea of electrons, where valence electrons are not bound to the particular atoms, metallic solids are very good conductors of heat and electricity. That's why the wires that we use for electricity at home are copper wires, because copper is a very good conductor of heat and electricity. Other metals are also good conductors, but copper is cheap, so we can use it in copper wires. Excellent. Okay, what do you think will happen? Think of the concept of the sea of electrons. What do you think will happen if we apply a force to metals? Would it break? Or would it only change shape? Okay, so if we apply force into metals, we can change its shape. Because think of it as marbles in water. Can we move the marbles in the water? Yes, we can, and it only gets like distorted, or that shape we can change them. So that's why we can make shapes with metals, like forming any kinds of shapes, like the faucet in your kitchen, or I don't know, I have here these needles. We can shape it to be needles or whatever shape that you need. Copper wire, we can hammer a piece of copper until we make it really, really thin into wires, because the sea of electron arranges or organizes itself. The electrons flow, and that's why metals are malleable. They can be molded into shapes. Okay, so metallic solids can also do alloys. They can form alloys. Alloys are mixtures of different metals, or metals with other kinds of atoms that are not necessarily metallic. We have different kinds of alloys. We have substitutional alloys or interstitial alloys. For example, here we have a pure metal. On this corner, we have a substitutional alloy in which the main metal it's introduced with another metal with atoms of similar size. And an interstitial alloy, it's the main metal, it's introduced with another metal or with different atoms of smaller size, filling these gaps, filling the gaps that are left by the general arrangement of the metals. So for example, an example of a substitutional alloy is brass. Brass is made of copper and zinc. As you know, copper has a high electric conductivity. So by applying zinc to the mixture, the electricity conductivity lowers. And brass, for example, is very easy, malleable, is very easy to make shapes, easier than the copper or the zinc alone. It has low melting point, and by changing the properties, we can change, by changing the proportion, we can change the properties. So this kind of combination is used for where we need low friction, for example, in locks and gears, when we have plumbing or electrical applications, or for musical instruments. And the reason is because we want less electric conductivity. We don't want to be playing an instrument and having static electricity into it. We don't want to have a lot of electricity flow in the plumbing. So that's why brass, it's a good choice. And that's a substitutional alloy because the main component, it's copper, and it's introduced zinc, which is atoms of zinc are similar in size to the atoms of copper, so we can change its properties as we change the atoms of copper we substitute them by zinc atoms. Okay, and that's an example, musical instruments. Okay, interstitial, as I mentioned, is where we introduce atoms of another metal, so for another things that fill the gaps. And the purpose in here, for example, steel, it's an interstitial alloy, and the base metal is iron, so iron will be represented by the red spheres. And carbon is not a metal, as you know, it's a non-metal. But by introducing carbon to this iron, it makes it harder. It increases its hardness. It's not as malleable, so it increases the hardness. And it is used, for example, in steel beams when what you want is the strength, because you want it to support a lot of weight. And also, for example, in railroad tracks. In fact, the story of the railroad tracks is very interesting. First, they used wood, but then they used only iron, and the iron they had to change it constantly because it was not strong enough. And then they started with these alloys of introducing carbon to the iron, and they have a great benefit of the railroad tracks now supporting a lot of weight in them, so they don't have to change them that often. So that's an interstitial kind of alloy. Any questions? Okay, we're going to move on. So in general, metallic solids will have, okay, let's compare it again to ionic. Will have a higher or lower melting and boiling points than ionic solids. Exactly, it will have lower melting points because they're very easy to melt, since the components are not so tightly bound together. Will metallic solids conduct electricity or temperature for that matter? Think of the wires, copper wires. Are they metallic or not? Exactly, you have this, correct. Metallic solids do conduct electricity and temperature because of the concept of the sea of electrons. Electrons are free to move around. And lastly, are metallic solids malleable or brittle? Remember that, can you make a shape out of a metallic cube? Exactly, they are malleable. You can shape them into whatever shape you like by applying force. Excellent. Okay, and the last one that we're going to see is where the atoms at the lattice points are, well, that form metallic solids. For example, we have diamond and graphite. Do we know which element forms diamonds or graphite? Which element of the periodic table forms diamonds? Okay, the element that forms diamond and graphite is carbon atoms. So in diamond, we have carbon atoms organized in this way, and each of these lines, it's showing a covalent bond. So diamond, it's very, very strong. In fact, it is used in the industry to drill other materials because that's how strong it is. And for example, graphite also has carbon atoms in the lattice points, but in here the difference is the arrangement. It forms like nets organized this way, and then another net above, another net below, and so on and so forth. And between the nets, what you have, like inside of the net, what you have is covalent bonds. But from one net to another, you have intermolecular forces. And as you can remember, intermolecular forces are weaker than covalent bonds or ionic bonds. So with this reasoning in mind, do you think would be very easy to break diamond apart or very hard to break it apart? Exactly, it would be very hard to break a diamond apart. But what about graphite? Would graphite would be easy to break? Think of the intermolecular forces right here. Exactly. Graphite will be easy to break, but we're going to break it in sheets, we're going to separate these sheets that are nuts are attached. So we're going to form like these thin films of graphite, because we will break them along the intermolecular forces. Excellent. So again, in general, will network solids will have high or low melting points. Can we generalize this in this case for network solids? Can we have a generalization for boiling and melting points? Well, the answer is no, because it depends on how the atoms are organized. For example, graphite will have a lower melting and boiling point than diamond, even though they both have carbons on their lattice points, but it depends on how it is organized. Okay, do you think network solids will conduct electricity? Think of the meaning of electricity. Could it move around electrons? Could it move around charges or no? Exactly. No, it won't be able to conduct electricity because there's no even charges in here. This is carbon atoms covalently bonded. There's no charges here. So no, it won't conduct electricity. And lastly, do you think they're malleable or brittle? Think of the structure. Could we break it apart? Yes, Rodolfo, we could break it apart. For example, graphite, we could break it apart in these thin sheets, as we mentioned. And again, it depends on the arrangement of the atoms. Graphite, it will be very hard to, diamond will be very hard to break it apart. But graphite would be very easily, and we're going to break it apart in these thin sheets. Okay. Very good. So we already covered all the content of this stream. So in a level of 1 to 5, how do you feel with this content? 5 meaning sure I could teach this, and 1 meaning no, I have no idea of any of this content. What score would you give to yourself? Okay, excellent. 4, that's easy. 3, okay, Rodolfo, so very, very easy to move on to a 5. So we just need to review a little bit more, but you have this. Okay, I'm pretty confident that you will ace your next quiz about this concept. Great job, everybody. Okay, do you have any questions? Because from my part, that's all. Any questions? Any last? Okay. Rodolfo, is anybody there? Okay. Thank you for your attention. You didn't quite understand brittle. Okay, Rodolfo. Brittle means when things break. For example, things that break versus things that are malleable. So malleable would be, for example, metals that you can make into these beautiful shapes like status of bronze. The artist is banging on the bronze metal until it molds it or shapes it into these different shapes. Or for example, the faucet in your bathroom, it's a metallic faucet and it's done by applying force to it. That's malleable. The opposite is brittle, when you apply a force and it breaks. Not necessarily melting, but shaping, because you're not making it a liquid. It's still solid, but you can shape it. You can distort it into shapes. And brittle would be breaking. Excellent. Excellent, Rodolfo. Any other question? Okay, thank you for your attention. See you next time. Bye-bye.